2, The Physics of a Falling Object. Introduction. The purpose of the lab is to observe and model an object from some height dropped from rest with some drag. We use the fundamental principles from Newton's second law, or the momentum principle. It says that force is equal to change in momentum over change in time. This helps us derive the velocity and position update formulas. The models I used were Excel, GlowScript, and Tracker. The result of the lab was to model how a wallet falls with gravity and drag acting on it. We used Tracker. The system was the wallet. The surroundings was the earth, which delivered gravity and drag. The initial conditions were that the wallet was dropped at a height of 5 feet and 8 inches, or 1.77 meters, at an initial velocity of 0. I calculated the height of the basketball rim off the ground, which ended up being 1.77 meters. As you can see on the right, the distance time graph for the wallet exhibits an exponential curve, which indicates an used GlowScript. This is the model that calculates without using drag. The ball's mass was calculated to be 1.6 ounces, or 0.0453592 kilograms. The ball's initial position and velocities were 0 respectively. The gravity constant was 9.8, and since this does not use drag, B equals 0. The net force is therefore, since there is no drag, the net force is only dependent on gravity, which can be calculated via the negative of the ball's mass times gravity. The ball's velocity update formula was calculated by the initial velocity plus delta t times F net over ball's mass. The position update formula is very similar and is calculated by the ball's position plus delta t times the ball's velocity. The clock was created as such so it can avoid rounding errors, since Tracker uses 30 FPS. When you run the program, you can see a negative exponential curve for position time graph as velocity is increasing at a constant rate. If you go into this is a model that uses drag. The ball's mass is the same. Honestly, everything is the same, except for the B is equal to 0.01. This is the coefficient, i.e. proportionality constant, for magnitude of drag force. Therefore, the way we calculate net force is much different. It seeks to calculate the drag force and adds it to the gravity. To calculate the drag force, we get the magnitude of the ball's velocity squared times the proportionality constant, plus the force of gravity, which is just negative ball's mass times gravity. The velocity and position update formulas are the same. The counter is the same. When we run the program, we get a very similar downward exponential curve, and the velocity again seems to be increasing at a constant rate. Here is the position v time graph generated by Excel. It shows the actual data, model without the drag, and model with drag. The orange line indicates the ball fell faster than it actually did, which makes sense as drag is a limiting force on downward acceleration, and removing it might make the ball seem faster. The actual and the model that predicts using drag are very similar. Any discrepancies might be because the actual wallet might have fell slightly in the x direction too, and the model only assumed a perfect vertical fall. What does it mean? Which model predicts a terminal velocity? If any, Model 2 is closer to predicting a terminal velocity as it aims to use drag and balance the effects of gravity on the ball with drag. This could create a net force of 0, as both drag is producing an upward force and gravity is producing a downward force. At terminal velocity, this cancels out to create a net force of 0. The terminal velocity would be the same. At the point of terminal velocity, net force is still 0, so it's impossible for it to be thrown to affect it enough. Look at the two graphs on the right. The one on the top indicates it being dropped from rest, and the one on the bottom indicates it being thrown downward at an initial velocity of what is negative 8.75 meters over seconds. Both end up plateauing at the same terminal velocity of negative 4.75 meters over seconds. This also proves why terminal velocity is not affected by initial velocity, as it can only be affected by the change in force over time.